here, this is a diagram. So by random conformal geometry, these are sitting in this box. And by that, usually I mean it's a two-dimensional in the continuum random systems. Examples, here's definitely not the exhaustive list, but just some example. There are Schramm-Levin evolution, conformal loop ensemble, Liouville quantum gravity, Gaussian free field, Brownian maps, etc. And a lot of studies about the link between the random continuum systems and with links to the discrete models. For instance, like random planar maps, statistical mechanics models, and or a combination of those. And usually it's taking the scaling limit from discrete random to continuum random. And my talk will be about another side, the other side of this story, from the continuum random system to a deterministic finite energy world. And by that, I mean, it's by considering some large deviation principle of these systems, and they will give rise to a lot of quantities that are deterministic, and they're actually of interest in other classical geometry, etc. And we can even do more. Then it can take a minimizer of those energy and getting to energy minimizers. So in random conformal geometry, the objects you see are often fractal. And when you take the large deviation, the objects, the finite energy objects, they will be more regular. And if you take energy minimizer, they're usually even more regular. They are smooth and even analytic. Just an example, the simplest one to illustrate. On the random side, continuum side, you have Brownian motion, and it is scaling limit of simple random walk. And the large deviation rate function of Brownian motion, this is by Schroeder theorem to give rise to functions with finite Dirichlet energy. And the minimizer of Dirichlet energy will be constant function. And if you just recall what Dirichlet energy means, is that if you have a function which is absolute continuous, you can look at its derivative, which is defined almost everywhere. The Dirichlet energy is just the L2 norm of its derivative. And we also set the energy, Dirichlet energy, to be infinite if it's not absolute continuous. Or in other words, this function is in W12. And we can already see these different regularity. For Brownian motion, you know that they are Holder continuous with exponent 1/2 minus epsilon for any arbitrary epsilon, a positive. But when you go to the finite energy function with Dirichlet, finite Dirichlet energy, they're actually 1/2 Holder. They're a bit more regular than Brownian motion. And if you take a minimizer, Dirichlet energy being 0, it means that the derivative has to be 0. The function is constant. Then it's an analytic smooth function. And to see that the finite Dirichlet energy imply a 1/2 Holder is just by Cauchy-Schwarz. And you write the difference of the function at 2 times, and it's can be written as the integral of its derivative. And by Cauchy-Schwarz, you get the factors square root of t minus x. So this is just a very simple illustration about this increase in the regularity when you go through the large deviation regime. So here I'm going to say about the plan of my 3 lectures. So in today's lecture, I will only be looking at caudal SLEs. And there are single caudal SLE and multi-caudal SLE. And there's a lot of other variants of SLEs. I won't be touching on that. And the large deviation rate function, they're called a Lovener energy or multi-caudal Lovener energy, depending on which model you're looking at. And for multi-caudal Lovener energy, we will see some relation to rational functions and also with other topics. In the second lecture, I will talking about SLE 0+ loops. And So here in orange, I just put on the relevant the random conformal geometry objects. There will be SLE loops, there will be Gaussian free field, loop quantum gravity, and also mating of trees. So in the second lecture, we will be looking at the case for Lovener energy for loops and some equivalent description of that. And especially it will relate to Dirichlet energy of some log conformal map. And in the classical geometry side, finite-energy loop will be called Weil-Petersson quasi-circles, and which ties links to Teichmüller theory. It's purely on the deterministic side. And the other, we will also be discussing some relation of in the coupling results in the random conformal geometry, including quantum zippers, imaginary geometry, and mating of trees result. And there's a dictionary towards some results in the finite energy world. So although the finite energy world, there are objects, they are deterministic, they are more regular, but from this lecture, you will see that actually there are many results in the finite energy world. It also reflects structures in random conformal geometry. And the proofs will be it's not the same, so it's not going from one side to the other. When I'm not going to prove those things, but just to show you there will be a very nice parallel story on both sides. In the third lecture, we'll be looking at SLE infinity in the radial case. And so which will give rise to an energy called Lovener-Kovarev energy. And on the finite energy side, the object that we, the classical geometric object, we'll be looking at their foliations of the Riemann sphere by Weil-Petersson quasi-circles. This is the plan of my 3 lectures. Yeah, so here are the references, and these are the number on the left. There correspond to the number of lectures that I will be discussing. So we will be talking about this paper and also the joint paper with Evelina today. All right, just to recall, I guess most of you know what they are, but still, if you haven't seen it, so to define the Lovener energy or the SLE, Kodo SLE, it is using a Lovener's transform. And Kodo means that it is a curve in a simply connected domain connecting 2 boundary points. And let's just first look at the case where the simply connected domain is the upper half plane and 2 boundary points at 0 and infinity. And if you have a simple chord from 0 to infinity oriented this way, and I look at the initial bit of the curve, and I look at the complement of this red initial bit, and there is a conformal map sending this green shaded area back to the upper half plane. And we choose the normalization of the conformal map such that it's asymptotic to identity map near infinity. And then this also, so we fix the constant term to be 0, and then this conformal map is unique. And the third term, here, this is a number which is always non-negative, and this is the capacity of this part of the curve. We say gamma is capacity parameterized if this conformal map always has 2t in this factor here. So the larger this part is, the larger t is, and there's a way to parameterize gamma in this way. And the tip of this curve will be mapped by gt to a real number on the real line, and is called the wt. And this function w is defined from r plus to r, is a real value function. It's called the driving function of gamma. And we know is that this function is 0 at time 0, and it is continuous if you start with a simple chord. Conversely, if you start with a driving function, a real valued function, you can also recover a growing family of how. But if you have this driving function comes from a simple chord, then you can recover this simple chord using the Lovener's differential equation. And in this case, we say that gamma is the Kodo-Lovener curve driven by the function w. So all this has been introduced by Lovener 100 years ago. And So it's not very important. If you haven't seen this, it's hard to grasp what it is doing. But if you haven't seen it, you just keep in mind that there is a way to write down, to encode the simple chords into a real value function. That will be sufficient for our class. Just a simple example that if the driving function is 0, then the curve generated should be just this imaginary axis. To see this, if you do you start with this curve and you look at the conformal maps, the tip has to be mapped to 0 because of the symmetry. And when the curve is driven by a random input, which is a Brownian motion times a factor square root of kappa, where kappa is some positive number, then the curve you obtain is called Schramm-Loeffner evolution, with parameter kappa denoted by SLE kappa. It's introduced by Schramm. And it is a curve, it's a very highly non-trivial result proved by Stefan and Oded. It's a curve generated by curve depending on different kappa. When kappa is greater than 8, it's phase failing. When kappa is less than 4, it's a simple curve. When kappa is between 4 and 8, it's self-touching. All right, and the example, the simplest example where the driving function is 0, this is just SLE 0. It's a deterministic curve. All right, now let us introduce on the finite energy side, our first player. It's called the Caudal-Loeffner energy. It is defined as follows. If you have a simply connected domain and two AB2 boundary points, you can find the conformal map from D to the upper half plane, sending A to 0, B to infinity, and gamma a simple chord, and it's going to be a chord inside upper half plane. And we just define the Loeffner energy of gamma inside the domain D from A to B to be the Dirichlet energy of the driving function of its image. All right, here this curve on upper half plane, then you can write down what this driving function is. And you can, we just define it, the Loeffner energy of this guy on the left-hand side to be the Dirichlet energy of the driving function of this curve on the right-hand side. And already here you can see that this to define this conformal map, you have some degree of freedom. Here you can still multiply by a constant positive number. You are going to scale the right-hand side. It's still good choice of conformal map phi. And we can actually show by explicit writing down what is the driving function. If you scale the right-hand side, how this driving function look like, we can check directly that this Loeffner energy, the Dirichlet energy of their driving function are actually the same. Which means that no matter which phi that you choose, this energy will be different, although the driving function will be different. The energy will be the same, although the driving function are scaled. So the Loeffner energy is well defined on the left-hand side. From our trivial example, that when the driving function has 0 energy, then it's equivalent to the driving function to be 0, constant is 0. And on the right-hand side, it's just this straight line up. And in a conformally invariant way to think about this is that this imaginary axis is the hyperbolic geodesic in the upper half plane. And using hyperbolic geodesic, hyperbolic metric, because of for simply connected domain, hyperbolic metric is the metric which is invariant under conformal automorphism. And so on the left-hand side, if you just say the Loeffner energy is 0, if and only if gamma is the hyperbolic geodesic in the simply connected domain D. Or you could just take as definition, being hyperbolic geodesic is the pre-image of the imaginary axis by this conformal map phi. All right, and if I have a finite energy chord, we can show that gamma is rectifiable. There are thousands of ways to prove this statement. With this definition of the Loeffner energy, this has been shown in a work by Fritz and Schickar. Already here, you see that there is a regularity, more regularity than SLE itself. For instance, SLE kappa, it was shown by Vincent Bofara that it has house of dimensions 1 plus kappa over 8. And being rectifiable, it shows that its house of dimension is 1. It's probably not very surprising. You will see it's relating to a kappa goes to 0 case, but still, SLE kappa, they're more fractal than finite energy curve. And this is being rectifiable is not this sufficient condition for energy to be finite, but it's not sufficient. There will be a characterization by F.A. Peterson quasi-circles. That will be the topic of the second lecture. All right, if there are any questions, please just interrupt. Or yeah. All right. So then I'm going to discuss the relation between SLE and this Lovener energy. In a physicist term, they usually call the Dirichlet energy as the action functional of Brownian motion. And in a finite half integral notation, they will write that, okay, Brownian motion, if I scale by square root of t, it has density is like exponential of minus the action over kappa times some Lebesgue measure on the space of function. All right, this is not making a regular sense, but there are other reasons, like to make sense of a Gaussian measure, this action actually is not hard to make sense of, but just literally, this thing does not make really sense, because as we see that for Dirichlet energy to be finite, it has to be held around half, but Brownian motion is never held around half. Dirichlet energy is infinity with probability 1, and also the Lebesgue measure on the space of function doesn't make really sense. But however, this identity somehow tells you that knowing things about the Dirichlet energy is going to tell you a lot about the Brownian motion already, as being the density of its distribution. And what the approach that I'm going to make sense of this identity is to use the large deviation. So this is Schroeder's theorem. Schroeder's theorem says, if I scale my Brownian motion by square root kappa and letting kappa go to 0, my probability of square root kappa times Brownian motion stay close to a certain deterministic function w, it decays like exponential minus the Dirichlet energy over kappa. When kappa is small, this is very large, the minus is very small, so it decays very quickly. And the Dirichlet energy is telling you how fast it decays to 0. And I will give you a more precise meaning in the setup of the SLE about the large deviations. So just using this interpretation and assume that we can apply Lovener transform to both of the functions. Here you get SLE, then here you get a finite energy Lovener curve. And we would like to say that the probability of SLE stays close to a certain deterministic curve. It decays with probability where the rate function is given by the Lovener energy of this curve. So the precise statement is the following. It has been first derived in my paper, the first paper, and the one here is stated in a recent paper with Evelina, where we endow the space of a simple chord, with the topology induced by the Hausdorff metric. So here we take the domain to be the unit disk, and there's a Hausdorff metric for a compact set on the unit disk. And in other domain, we will just use the topology that's by pushing forward using conformal map. And the statement is following: the law of the SLE kappa satisfied LDP with good rate function, the Lovener energy, which means that if you take any subset of the space of simple chord, the lim in for this probability of SLE belong to the interior of A. We take log and kappa when kappa goes to 0. it's bounded from below by minus the infimum of this rate function for all the elements inside the interior of A. And this inequality is a trivial one. I replace A interior by the closure of A, and the lim sub is also bounded by minus infimum of the of gamma belonging to the closure of A of the Lovener energy. But when we say that ID, the Lovener energy, is the rate function of this family of laws, it means always that a similar inequality holds. And being a good rate function means that the sublevel set, where all the cores with energy less than C is a compact with respect to topology that we have. So topology here is important because when we talk about closure and interior, it depends on which topology that you're looking at. And more precisely, how to think about this result. If you take a set A to be an epsilon neighborhood of gamma, so this collection of all the gamma prime whose Hausdorff distance to gamma is less than epsilon, you can, using some monotonicity argument, to see that for only with countable exception of epsilon, this side, this inf, will be equal to the inf of its closure. All right, and if they're equal, then this lim inf and lim sub, they're just equal. And what you obtain is that the SLE kappa belonging to the epsilon neighborhood of gamma is decaying like exponential of minus the infimum of the Lovener energy of gammas in the epsilon neighborhood, the gamma prime in the epsilon neighborhood of gamma. And if epsilon is really small, this infimum is also very close to the Lovener energy of gamma itself. So the way to think about this is that probability of SLE kappa being in the epsilon neighborhood of gamma is decaying like exponential minus the Lovener energy of gamma over kappa. And yeah, here are the pictures of illustrating whether the epsilon neighborhood means in the unit disk, and we can talk about the topology in the Abrahamov plane just by pushing forward. So the neighborhood will look like this. We're going to cover infinity when you map to the Abrahamov plane. All right. So using this interpretation, we can show a result purely deterministic. We have that the Lovener energy is reversible. By that, I mean that if I consider the same curve and I invert the boundary point A and B, I would get their energy are the same. If you think about the definition of the driving function is defined in a very directional way, and there's no simple reason to compare the driving function of gamma and the reversed gamma. So, but however, this is still a deterministic result. It's just about Dirichlet energy of two functions. They're equal. And using the interpretation with SLE and also the very strong result about SLE reversibility by Chen, which also derived by Miller Sheffield in different methods, that when kappa is less than 4, I'm stating the result from Chen, that the trace of SLE kappa in DAB is the same as the trace of SLE kappa in the reverse setup. So here the trace means that you just consider the points visited by SLE, but forgetting about the time parameterization. And well, okay, how to derive from SLE reversibility to energy reversibility? It just says that, okay, when kappa goes to 0, the probability of SLE kappa stay close to gamma is the same as if the reversed SLE kappa stays close to the reversed gamma, because the Hausdorff metric that we take is also invariant under this inversion. Okay, so it seems the probability are the same, and SLE also has the same law with this reversed one. They have the same decay rate. And the same decay rate gives you that energies are also the same. All right. One might wonder, so this is like using a probabilistic proof to prove something that is deterministic. And we will also give another proof in the second lecture. So we are going to give some intrinsic the interpretation of this energy, and which does not rely on SLE later. All right, so this is about single SLE, large deviation. And let's move on to multimodal SLE. It's slightly more general than single SLE. And the multiple SLE that is coming from multi-interface second mechanics models. So for second mechanics model, which you can put like alternating boundary condition. Say here, this is a simulation of the critical easing by Evelina. And then conditional this interface, say, this interface will just be a interface inside this domain with just two different boundary conditions. And therefore, this curve has to be the SLE3 here. So in the case of a multiquadral, there are more choices in how these boundary points, two end boundary points, will be paired together. And here we just illustrate some link patterns and corresponding to each of those. From consideration of the statistical mechanics model, it is natural to define multiquadral SLE and the following way. So we fix alpha as a planar link pattern. It means that it's going to pair up your two end boundary points in the way that they're not going to cross each other. And we can count that how many are there. There are a catalog number of those link patterns. The multiquadral SLE is characterized by this curve gamma j for each of the j belonging to the n chords, such that it is the SLE kappa in the union of the faces adjacent to it. So that's a conditioning on all the curves. This curve has to be the SLE kappa inside the gray shaded area. Has been studied by many groups of people, and the existence and uniqueness of this law, just here is by characterization, and the existence and uniqueness are obtained for kappa belonging to 0 and 4. And somehow, for when kappa equal to 0, the natural definition of SLE0 would be that each of this curve has to be the hyperbolic geodesic, has to be the SLE0 in this gray shaded area, which is the hyperbolic geodesic there. And therefore, we just defined that a multichordal SLE0 to be the geodesic multichord. It means that each curve is the hyperbolic geodesic in the union of the two faces adjacent to it. It should be a deterministic multichord. This for kappa equal to 0 in the single chord case, it seems to be the simplest case. But however, the uniqueness in existence is not completely trivial. The reason for that, the results, the uniqueness and the existence works for 0 and 4, is because that the multichordal SLE can be obtained by weighting this factor, weighting an independent SLE by this factor. So what are these? C of kappa, this is the central charge related to kappa. So we will only be looking at kappa equal to 0 case. It's asymptotically minus 24 over kappa. Okay, already when kappa equals to 0, it doesn't really make sense. And also, when kappa equals 0, there has to be a deterministic curve, so there's no radon-Nicodim derivatives, which will make sense. And here, this is the formula for the radon-Nicodim derivative when kappa is less than 8/3, where the central charge is negative. When central charge is positive, there will be also an indicator function where the curve, you have to restrict to the curve those who don't intersect each other. So it doesn't matter here. And what is this M? M is a quantity that is expressed in terms of Brownian loop measure. And for those who knows, so explicitly can write it down as the sum from 2 to n to the Brownian loop measure of loops which intersect at least p chords. We take the sum from 2 to n. So the takeaway is that the first thing, if n equals to 1, this sum is 0. Also, it makes sense because you are weighting by nothing if you're just one chord. And also the other thing is that if the chords are disjoint, this has to be finite. Also, this is something that is positive because this loop measure is positive. And moreover, this quantity is conformally invariant because the Brownian loop measure is conformally invariant. Okay, you just think about this is quantity associated to the multi-chord in a conformally invariant way. All right, and now we are going to tackle this problem that what is the multiple SLE0? What is the geodesic multi-chord? So we did this with Evelina. The proof is very cute that we're going to associate to a multiple SLE0 with a rational function. So first of all, the SLE are defined in a conformally invariant way. We just take the domain to be either the disk or the upper half plane. Here we take the upper half plane. We prove the following result that if eta is a geodesic multi-chord for a given connection pattern alpha and the boundary point x1 to x2n, the union of etas and their complex conjugate in the real line is the real locus of a rational function of degree n+1 with critical points, those 2n points. The rational function, it just means it's a ratio of two polynomials. And how to construct this? We're just going to use the assumption that this is a geodesic multi-chord. The construction of the rational function is the following. I start with, on this picture here, eta are here. This is the real line. And here, this is not well drawn reflection of it. This is a complex conjugate of eta. They're supposed to be symmetric. Okay, so what to do is to take one face of it and map it, take any conformal map, sending this to the upper half plane. Now, this chord will be mapped to somewhere on the real line. So all this, I will view this on the Riemann sphere, so it doesn't matter it's infinity or, you just assume that it's here. This chord mapped to this part. And now I consider the conformal map of the union of these two faces to the union of the upper half plane and lower half plane union this red curve by sending the two endpoints to the two endpoints. Because this red curve is a hyperbolic geodesic, it has to be mapped to this part as well. Therefore, we can actually extend this original conformal map from orange face to the upper half plane across this red curve to the lower half plane, which becomes a it's a holomorphic function defined on the union of these two faces. We only use the fact this curve is the hyperbolic geodesic in the union of the two faces. But then we keep doing, this part will be sent to the lower half plane again, this will be sent to the upper half plane. Keep reflecting. And also we notice that the real line is always being mapped to the real line. Therefore, by Schwartz reflection, you can extend this map again to the lower half plane. And now these are mapped to the upper half plane, lower half plane, lower half plane. All right, so in most of the, it is locally always 1-to-1, apart from you're at those points here, where it would be 2-to-1. And that is what critical points would mean. And its degree n+1 says that if you look at the generic point here, and how many pre-image it has. It has 1, 2, 3, 4. Has 4 pre-image. This is the degree of this rational function. So we start from geodesic multichord. We constructed a rational function. And what are these multichords? They're just the pre-image of the real line by this rational function. All right, then the question of looking for geodesic multichord will become just looking for a rational function with given prescribed critical numbers, critical value, critical points. And we will use a result by Goldbach and proved using algebraic geometry method. Is a question in algebraic geometry that if you're given two n distinct complex numbers, they're not necessarily real. She showed that there are at most a catalan number of rational functions with degree n+1 and prescribed critical points. So of course we can also post-compose with a PSL2C map, which is a conformal automorphism on the right-hand side, a fraction linear function. It is still a rational function with a critical point, the same critical point. So one have to modulo out PSL2C post-composition. Right, this is Goldbach's work. So assuming we have the existence of geodesic multichord, then for each alpha, we will find one rational function with those prescribed critical points. And also there are a catalan number of linked patterns. So we find already all of the catalan number of equivalence class of rational function. And moreover, in our case, we are looking at the case where the critical points are all on the real line. So as a consequence, we show that if these all these points are on the real line, then you can not only be bound, the number is bounded by Cn, but actually you already obtain a catalan number of rational functions. And another corollary is that if these critical points are all real, then the function is actually equivalent to a real rational function. By real rational function, I mean that the coefficient of the PMQ are all real. And you can see that from this construction, it's explicit. And it's mapping the real line to the real line, so the coefficient has to be real. So it shows that if your rational function has critical points all real, then it's a real rational function in the equivalence class. So this result is actually first proved by Eremenko-Gabrielov, appeared in Annals of Mathematics. But here it will be also, here we obtain an analytic, another proof of this result. So their work is also based on Goldbach's estimate, the of Goldbach's bound. So here, I didn't prove for you why it exists, but once we have the existence, you have the uniqueness of the geodesic multichord, you have also this corollary. So for the existence, it is obtained by minimizing a certain multichordal Lovener potential. So by multichordal Lovener potential, it is given by defining the following way. It is just taking the sum of the Lovener energy divided by 12 and plus a term which is coming from the Brownian loops, which is also the term inside the Radon-Nikodym derivative of the multiple SLE. And there's a last term is the Poisson excursion kernel about the boundary point. It does not depend on chords, only on the boundary point. And the reason of including this is to, in fact, we're going to relate this potential with different boundary data. And also by including this quantity, it will give you a nice formula in terms of deterministic Laplacian. And when n equals to 1, this Lovener potential is just simply this way, written this way, and especially it minimized for fixed boundary data. It minimized only if the Lovener energy of gamma is minimized, which means it is hyperbolic geodesic. So this is a potential for multichord. And some characterization property about the potential Okay, so it is the first. This one is the cascade relation. It says that if I have my multi-chord potential of the n chord can be given by if I consider n minus 1 chord, the potential of the n minus 1 chord, and plus the Lovener potential of the last one, but only in the gray shade area. This is the dj hat. So this holds for any j. You can do this. And so if we consider a minimizer of this potential, then this second term does not depend on gamma j. Only the first term depends on gamma j. So it has to minimize the first term. The first term is minimized only when gamma j is hyperbolic geodesic in d hat j. And this relation also holds for any j. Then it shows that any minimizer of this h, the potential has to be a geodesic multi-chord. And to show that this minimum is attained, so the way that we prove it is to consider minimizing sequence, and you have to show that you can extract subsequence which actually converging to the limit, a limit which is a multi-chord and with the Lovener potential, this minimum. All right, so and to show that we use some machinery from quasiconformal mapping by studying this Lovener potential. Essentially, quasiconformal maps are used only for giving you a capacity result. Which let's see. Right. Once we have the minimal the Lovener potential, we can define the Lovener energy. But we define first the minimal potential as being it's a function depending on alpha and the boundary point, and it to be the minimum of this Lovener potential. All right. Also, here I just have to say that just to put the period to the previous discussion with the Goldbach's result, that here with this corollary we have the existence of the geodesic multi-chord for each of the connection pattern alpha, and which therefore then complete the proof of existence of multiple SLE0 and uniqueness of multiple SLE0, and also a proof of the work is called the Shapiro's conjecture of the work by Eremenko-Gabrilov, showing that if your rational function has a real critical points, only have real critical points, then it has to be a real rational function. Yeah. So the Lovener energy that we define is to be the difference of the Lovener potential minus its infimum, especially when you take out this infimum, this Lovener energy is non-negative. And when you take n equals to 1, this energy coincides with the single chord Lovener energy. And the large deviation also holds the same. This is also done by with Peltola, Evelina. That if we endow the space of multi-chord with the product topology induced by a Hausdorff metric, then the law of multi-chordal SLE curve with this connection pattern and the boundary data satisfy the large deviation principle with good rate function, this Lovener, multi-chordal Lovener energy. And the proof is using the Radon-Nicotian derivative of the multi-chordal SLE. So first you have LDP for a single SLE that we prove. And then if you take independent SLE, n of them, what you do is you take the product of their density and their rate function will just be summing up. So in this case, gives you the term why we have this sum here. Oh, sorry, summing up the the Lovener energy. And then there's the second term coming from the radon-nicotine derivative, giving you the interaction between those SLE. And you pick up this point. And so that is essentially the proof. And the last term is not relevant for a large deviation for fixed boundary data, because if you look at the minimizer, this doesn't depend on the chord. If you take the minimizer of this guy, this term will just be canceled out when you take the difference between the Lovener potential and the minimal potential. Oh, that's why. So here I basically explain in the proof that the single one gives you the first term in the potential, the second one gives you the second term in the potential. So I still have very quickly explain that why do we want to include the Lovener, the Poisson kernel term inside the Lovener potential? There are two reasons. The first one is going to relate different boundary data. This is by this result that this is just a shorthand notation for an alpha times 12, the minimal potential. It's the following theorem. It says that if I look at my energy minimizer, this unique geodesic multi-chord inside with boundary data alpha and equal to x2n, then I can write out what is the Lovener driving function of each of those curves, and they're given by a partial derivative of the Lovener the minimal potential. And this is only true if you include the Poisson kernel term, which compares different boundary data. Then you have this partial derivative, which making sense. And you don't have to read this theorem. And the idea is just, the statement is just that if assuming this orange curve is my geodesic multi-chord, and then I map out the first bit using the same normalization at infinity with the conformal map, then all the points will be moved. X1 is to move to VT I, and the tip of this point will land on WT, and WT is the driving function of this curve. And this WT satisfies this differential equation. And this is similar to, in SLE, there is this result where U is replaced by a partition function of SLE. And another result relating, so this partition function of SLE, we can show is that this U is exactly the limit when kappa goes to 0 of minus log of the partition function of SLE when kappa goes to 0. And we can derive a system of partial differential equation about this Lovener potential relating different partial derivatives. And this is actually a semi-classical limit of Belavin-Polyakov-Zamolodchikov, one of them for SLE. And you can guess this equation if you know what is those equations satisfied for SLE. But our proof of this result is by direct analysis of the minimal potential, and the proof is quite short and direct. So a related question is that if you think about this minimal potential for a given boundary data, there's always a rational function that is lying behind. They're just a function that's having a rational function with those points as a critical numbers, or critical values, or critical points. Yeah, and here you have a relation between the minimal potential set for a certain family of differential equation, and it'd be interesting to relate more explicitly this minimal potential to the associated rational function. And we have no clue. It will be very interesting to know how to do this. Okay, so these are telling you that this minimal potential is actually capturing some the relation between the potential of different boundary data. And here, this is the last slide, I think. Yes, the last slide, almost the last slide, about the how the Lagrange potential. The other reason for including the Poisson expression kernel, that is, with that Poisson expression kernel, then our Lagrange potential has a very simple expression by taking the deterministic Laplace, log deterministic Laplacian of the whole domain Z, and take out C are the connected components of the complement of this chord, each of the faces. When you take out the log determinants of Laplacian of the faces. And there's some universal constant that one can compute, but we didn't. So then it gives you a very simple expression about Lagrange potential in terms of log determinants of Laplacian. And the relation between deterministic Laplacian with SLE has been observed by Dubeda, Fevich, Kontravich, Suhov, many people working on this, also in relation to Brownian loops, and etc. So these are not completely surprising to see this expression. But however, we're happy to see it's very clean and neat and simple here. Okay, so this is all I wanted to say, and that's it. Thank you for your attention.
Any questions? So I have one question. Can you comment on this constant lambda?
Oh, lambda? Yeah. All right. So what we know is that so this lambda is the same. Lambda does not depend on anything. Lambda is a universal constant. So to compute the lambda, one can, for instance, consider d equals to d, and say I take just this case. You have a half disk, and in this case, what we have, one can compute explicitly what is this guy. This is like 1/12 of the Lagrange energy, which is 0. And then there is a term 1/4 log of the Poisson kernel. So these are all explicit. And then we just have to explicitly compute what is the deterministic Laplacian of the unit disk and the deterministic Laplacian of the half disk. And you can find out what is this lambda.
So, okay, there's a way of computing it. I see.
Yeah, it's just, yeah. You probably, if you need to find some nice, simple. Yeah, maybe it's easier to just, yeah, that's just do the square where you have all this all the eigenvalues are explicit, and you cut it in half.
I see.
And compute the lambda.
I see.
Yeah.
And also, can you comment on the existence or uniqueness of multiple SLE when kappa is bigger than 4?
I think it's a claim to. I think Bendelin has claimed to have that, but I haven't looked at it.
Okay.
For when kappa larger than 4, I think there's also a proof. I think they did in the case of n equal to 2, but I guess that in the other end, this should be not a very hard generalization.
And so one final question for me is, what's the meaning of a real locus for the rational function?
Oh, right. Okay, yes.
Yeah, what's the definition?
It's just a pre-image. I should write this down. Yes.
Yeah.
So this is just, if I call this f, this function, the real locus is f.
Okay, I see.
Yeah.
And in your theorem, the real locus of this real line is given by the union of the real line and all these circles?
Right. This is given by eta, its complex conjugate, and the real line.
Okay, I see.